Hi, my name is James Hoyt, and I will be a senior in aerospace engineering at the University of Michigan. This summer, I participated in the SURE program researching air-breathing electric propulsion in Alec Gallimore's Plasma Dynamics and Electric Propulsion Lab. The research started with doing simulations of a satellite in low Earth orbits to determine the effects of pressure, drag force, velocity, exit velocity, mass flux, and density on the satellite. The simulations were run with a number of different orbit parameters. After an analysis of the simulations, it was determined that air-breathing electric propulsion is feasible for low Earth orbits. Additionally, literature suggests that a radio frequency plasma source, specifically the ion beam from a helicon plasma source, is a promising phenomenon to be used in air-breathing electric propulsion systems because it operates well in the conditions presented in the simulations. If we take a closer look at this graph is an example of the analysis of the simulations. The simulations were run in STK, the satellite toolkit. STK has the ability of outputting many different reports, such as the satellite's velocity, satellite's altitude, and the atmospheric density and the atmospheric pressure. Using these reports, MATLAB plots like the one shown here for the drag force, mass flux, and exit velocity can be made. This plot is an example of the drag force versus altitude, where the drag force was calculated using the equation F equals 1/2 CD A rho V squared, where CD is the coefficient of drag, and that is a user-defined quantity in STK, and in our case it was 2.2. A is the incident area of the satellite, and that is also a user-defined quantity in STK, and in our case that was 1 meter squared. Rho is the atmospheric density, and that is a STK report, and V is the satellite's velocity, and that is also an STK report. The PEPL facility consists mostly of the large vacuum test chamber, which is a 9 meter long and 6 meter diameter vacuum chamber shown in this picture here. Not shown in this picture is the smaller vacuum test chamber, which is on the other side of the large vacuum test facility. Located throughout the facility are many smaller pumps and vacuums, which are essential for pumping the chamber down to its vacuum conditions. The large vacuum test facility is the best facility for testing plasmas and thrusters because of its size and the additional available instruments for measurements, such as the probe diagnostics, which allow for the measurement of plasma properties. My first project at PEPL was a facility upgrade project, and it was my introduction to the lab. My job was to improve the exhaust system of the smaller vacuum chamber. As you can see here, there are two ports, this port being for the gas recovery system and this port being for the oil mist filter. My second project dealt with the data acquisition system. Electrical information is very important when taking diagnostic measurements. Therefore, a data acquisition system was already in place. I improved the user-friendliness of the data acquisition system by machining the enclosure shown in this picture. As you can see, this front panel consists of 20 B and C connectors to connect to the modules. The side panel has an Ethernet connection here to connect to the brain, to the computer for LabVIEW interaction, and an AC power connection here for the power supply. Also, the enclosure has an easily removable top for easy access to the modules to modify or change the modules. The goal of my current project is to use sensors to get a more accurate measurement of the RF power from the helicon plasma source, and from that, a more accurate estimation of the efficiency. In all thrusters, efficiency is a very important measurement and can be represented by this equation here. If we look at Pn in this equation, it is a function of RF power and DC power. It is very difficult to get an accurate and repeatable measurement of RF power due to power reflection at impedance boundaries. Because of this, the efficiency of a helicon plasma source is a hotly debated topic in literature. Currently, we use a transformer, shown in this picture here, to measure the RF power from the helicon plasma source. My goal is to input sensors into the system to get a more accurate measurement of the RF power. I would like to take this time to thank the SURE program, Alec Gallimore, and the graduate students at PEPL for giving me the opportunity to conduct this summer research. Thank you.